Section 3.5 is entitled Limits at Infinity. And obviously the reason why is you're going to be heading towards either infinity or negative infinity with your limits. And so what you want to do is you want to look at what we call the degree, or the largest exponent, of the numerator and of the denominator. Up here in the numerator, you can see that the degree is 3, that's your largest power, and the denominator, it's going to be squared, or a 2. Now you may remember from Honors Pre-Calc that the rule for x approaching infinity is real simple. If the numerator has a larger degree, which in this case it does, the answer is going to be infinity or perhaps negative infinity in certain cases. And so the answer right here is going to be infinity. If there had been a tie, let's say that the denominator was 4x to the third instead of 4x squared, then you would simply strip the coefficients off the greatest degrees, and you would have an answer of 1/4. And finally, if the denominator had a larger degree, let's say that it was 4x to, say, the fourth instead of squared, then the answer would be 0. And now that we're a little bit more advanced than we were back in Honors Pre-Calc, we can see why with a couple different ways. Again, going back to Pre-Calc, you could take all 6 terms and divide them all by the largest power, which in this case would be x to the third. If I was to do that, I would arrive at this. Now when you let x become infinity, all these become infinities. 1 plus 0 plus 0, which of course is 1. And down here in the denominator, you get 0 plus 0 minus 0, which is 0. And you can think of 1 out of 0 as kind of like being a bonus point. You're going to approach infinity. Now, of course, I realize you're not allowed to divide by 0, but technically we're not dividing by 0. These aren't really zeros. They are near 0 because x isn't equal to infinity. It's approaching infinity. So, regardless, you've got infinity as an answer. So that's one way to explain it. Another way, now that you guys are in calc, is you could use L'Hopital or L'Hospital's rule that we just learned from section 8.7. As you can see, if you plug the infinity in, you would get infinity over infinity, which is an indeterminate form. So we'd start by taking derivatives of the numerator and denominator. Taking the derivative of the numerator, of course, would be 3x squared plus 5. The denominator, in turn, would be 8x plus 2. You can see that that is still going to be infinity over infinity, so we take another derivative. That'll end up being 6x over 8. Now, when you plug the infinity into here, 6 times infinity divided by 8 is still going to be infinity. So L'Hopital's rule will work as well, and that's probably the quickest way to do these. That's the reason that the shortcut in Honors Pre-Calc works, is because L'Hopital's rule is behind the scenes.
Here in number 2, the degree of the denominator is actually larger. The numerator's degree is 4, that's pretty obvious. The denominator looks like it might be 3, but it's actually 5th power. As a result, the limit as x approaches infinity is simply 0.
Number 3, we have a degree that's the same. Both of them are 7th powers. You're heading towards infinity, so the answer is simply 3/5. Here in number 4, it's a little bit tough to tell what's happening. I'd like to rewrite the denominator. Let's face it, if x is heading towards infinity, that minus 2 isn't going to matter. You're going to have 9 times infinity squared. Even though you're square rooting it, who cares if you lose a 2? So really, you're looking at just the square root of 9x squared, which happens to just be 3x. And now when you look at the problem, you can see that obviously the limit here is 6/3 or 2. Okay, number 5. Don't worry about the trig. You see that we have sines and cosines involved, but when you think about the graph of sine and cosine, they never really go that crazy. In fact, they stay 1 unit away from the x-axis their entire lives. So really, when you head out towards infinity, or in this case, negative infinity, these aren't really going to matter much. They're going to stay between 1 and negative 1, so what? You can really basically ignore them and just look at what you have over here. 12x over 8x, even though x is negative infinity or heading towards negative infinity, the x's are going to cancel each other out. So the answer would be 12/8. Obviously, I want you to simplify that. You can divide them both by 4. And so here we're going to get 3/2 or 1.5. Okay, now we have to pay a little bit more attention to the fact in number 6 here that this is approaching negative infinity. I've been a little sloppy so far, but now we're going to be a little more careful. You can see that the degree in the numerator is higher. 9 beats 6. And so what happens is we're going to have an answer that's either infinity or negative infinity. Now, of course, you don't want to miss this because your mistake would be the largest mistake known to mankind if you have, say, infinity instead of negative infinity. So we do have to be a little careful here. Think about this. These aren't going to matter. It's simply 2x to the 9th over 3x to the 6th. I can cancel away 6 x's, making that just, 2x to the 3rd up top. Now think about what this looks like when I head towards negative infinity. I'm going to have an odd number of negatives, and negative times negative times negative is negative, of course. And so the answer will be negative infinity. The 2/3, of course, is not going to make any difference. 2/3 of negative infinity is still negative infinity, as weird as that seems. So basically, the shortcut here is to, if you realize that the numerator is going to win out, and certainly here it does, 9 is obviously larger than 6, you know it's going to be either infinity or negative infinity, simply subtract the 9 and 6. 9 minus 6 is 3. Since 3 is an odd number, you're going to have an odd number of negative signs, and therefore the answer will be negative. If it had been 2x to the 8th up top, 8 minus 6 is 2, that's an even number, that would be positive infinity, because the 2 negatives would cancel. In fact, here's a perfect example of that. We have 3x to the 10th over 8x to the 4th. Obviously, we don't need this part of the problem if you're heading up to negative infinity. 10 minus 4 is 6. If you strip this down, there would be 6 negative signs in the numerator. That's an even number of negative signs. So even though you're heading towards negative infinity, this limit is going to be positive infinity. Okay, number 8. Don't let the parentheses mess with you here. Let's look at this piece by piece. That green square as you head towards infinity is going to be 1. Over here, in this red rectangle, that's going to end up being 9 because, the third powers match. So really, overall, we have 6 plus 1, 7, times 9, which, of course, is going to be 63, our final answer. Again, a lot of times it's easy to get sidetracked. A lot of people will have 9 instead of 63 because they'll forget that the 6 was here. So, just be careful. Now, with number 9, you may be wondering, what is this problem doing here? It's supposed to be limits at infinity, and you're plugging in a 0. But if you do plug in a 0, you're dividing by 0, or something very close to 0. It won't truly be dividing by 0 because there is a minus 1 down there. Let's try this up top. So what's going to happen is you plug the 0 in, you're going to get 0 plus 3, which is 3. Down low, you're going to have, 0 minus 1, that's negative 1. And voila, the answer is negative 3. Now, of course, if the minus 1 was not there, if this hadn't happened, you'd have 3 over 0, and then we'd have different issues that we'd have to look at. In that case, you'd be dividing by 0. It's possible that the limit may not exist, so obviously we're going to see some problems like that coming up. In number 10, I look at this thing and immediately I know that the answer is going to be 0. Of course, why, you ask? Well, here's why. We've already seen that sine and cosine are sort of homebodies. They're not going to stray much from the x-axis. In fact, they're not going to go more than a block away. Even if you put the negative infinity in, cosine of negative 2 infinity is still going to be between 1 and negative 1. So I'm simply going to write near 0. And again, I don't know what's happening in the denominator except it is growing extremely large and negative. So if you had like something near 0 over negative infinity, that's going to be 0. And we don't worry about positive divided by negative or what the sign is, because 0 and negative 0 are the same number. They're both 0. So that's the answer. So again, we're using the fact that cosine doesn't stray too far from the x-axis to kind of help ourselves out a little bit here. In this problem, the a is meant to be a constant, and x is approaching a. X is approaching that constant. A lot of people kind of flip out when they see that second variable. They're like, oh boy. But you don't have to make this tougher than it is. In fact, I see the opportunity to factor here. I'll start with the denominator. X to the fourth minus a to the fourth, I can use difference of squares. That'll be x squared plus a squared times x squared minus a squared. Okay, so that got rewritten. Now at this point I could continue to factor, and some people will, but honestly that's a waste of time. If you notice that canceling can occur immediately, I have a pair of x squared minus a squareds available. I'm just going to cancel them out, make them both 1s. And now my dividing by 0 issue that I had originally is no longer there. I can use the x approaching a right now and get my final answer. Obviously, you're going to have a 1 up top. A squared plus a squared is 2a squared. And so the limit, as x approaches a, is 1 over 2a squared. This is by far the most difficult problem that we're going to do. The problem here is L'Hopital's rule, we don't really know enough about it. We're going to learn more L'Hopital or L'Hospital's rule in Chapter 8. I just briefly introduced it at the end of Chapter 2. But if you plug the infinity in, you're going to get infinity times the sine of 0, which is 0. Now, in the world of multiplication, infinity and 0 are both superheroes. What I mean by that is, infinity is an undefeated champion. Infinity is like, oh, you're going to multiply by me? The answer is me. And 0 is like, well, you haven't met me yet. Anything times 0 is 0. What happens when these two immovable forces go to battle against each other? Is infinity times 0 0? Or is it infinity? Or is it something else? And the answer is, we don't really know. And so I can't use my normal math intuition here. It's not going to work. Infinity is just a weird exception, and really, honestly, so is 0 in many cases. So instead, I have to figure out a way to rewrite this problem. Just for fun, I'm going to throw a 1 underneath the x and turn it into a fraction. And then I'm going to pull a little substitution. I'm going to put in a different variable called u, and I'm going to let u equal this 1 over x right here. So what happens then is we have sine of u. This is x over 1. U is 1 over x. So therefore, this would become 1 over u. In fact, I'm just going to write this as sine of u over u. All right, we're taking the limit as x approaches infinity. But if x approaches infinity, again, look over here, u would approach 0, 1 over infinity. So really, we're taking the limit as u approaches 0. Now, I don't know if this looks familiar from earlier on in our calculus knowledge, but remember, when you're near 0, the sine of something over the same something is going to be equal to 1. And that is the answer to number 12. So you heard it here first. 0 times infinity is 1. Will that always be true? No. And you're going to see that in Chapter 9. 0 times infinity could be a whole host of different answers, so it's indeterminate. All right, so there you have it. Limits at infinity.